Here we have another example of where we're trying to find a confidence interval for an unknown population mean mu. The Wind Mountain archaeological site is located in southwestern New Mexico. Wind Mountain was home to an ancient culture of prehistoric Native Americans called Anasazi. A random sample of 15 excavations at Wind Mountain yielded a mean depth of 74.2 centimeters and a standard deviation of 18.3 centimeters from present-day surface grade to the location of the significant artifacts. Assume the depths are approximately normally distributed. Compute a 95% confidence interval for the mean depth mu at which archaeological artifacts from the Wind Mountain excavation site can be found. Interpret your results. With our previous example, we looked at weights of hummingbirds, and in that computation, we used this formula here as our way to compute the margin of error, the critical value associated with the standard normal curve times sigma sub x bar. I claim in this particular problem right here, you cannot use this formula. Why? And if you're not sure immediately why, let's first write down the values of all these numbers. So what variables are associated with each of these numbers? So a random sample of 15 excavations, that's our sample size, so n is 15, at Wind Mountain yields a mean depth of 74.2 centimeters. So that 74.2 mean depth is for those 15, so it's the sample mean, not the population mean. If it was the population mean, then we wouldn't even need to do this. And a standard deviation of 18.3. The 18.3 centimeters, again, is still talking about these 15 excavations. So just to read it one more time, a random sample of 15 excavations at Windy Mountain yielded a mean depth of 74.2 centimeters and a standard deviation of 18.3 centimeters. So that standard deviation, 18.3, is a sample standard deviation, which is represented by the lowercase letter s. The only other numeric piece of information we have here is 95% confidence interval, so we know that C has to equal 0.95. So now let me ask this again. Why can we not use this margin of error formula for this problem? Take a moment to think about this. Hopefully you recall, in order for us to use this margin of error formula from our previous video, the population standard deviation sigma needed to be known, and the sample size had to be greater than or equal to 30, or the population had to be normally distributed. But right away, the population standard deviation sigma had to be known. We do not know sigma. Remember, population standard deviation is this Greek letter sigma, and the sample standard deviation is lowercase s. This 18.3 is s. It's a sample standard deviation. It's not the population standard deviation. So this new video, we are going to start to look at developing confidence intervals when sigma is unknown, which is very common. You're not likely to know sigma, the population standard deviation. So how can we actually approach a problem like this? You may be thinking, why can't we just use the sample standard deviation as an approximation of sigma, the population standard deviation? But it turns out there's an even more accurate way of doing this. And some time ago, a man named W.S. Gossett figured out that we need something called the t-distribution, which is another probability distribution, to answer a problem like this. Let's take a look at that distribution. The t-distribution is defined by the following. This forms a t-distribution when the x distributes approximately normally or normally. You don't have to worry about this definition so much here. What we do need to know, though, is a bunch of the important key features of the t-distribution. So first, for reference, look at, we've got multiple curves here. This blue one is the standard normal distribution. These other colored ones are several different t-distributions. You'll see there are multiple t-distributions that we need to talk about. So first, the t-distribution is in fact a probability distribution function. It's a continuous probability distribution function. So just like the standard normal distribution, it also has a total area underneath of 1. And notice that these three curves in here, the red, black, and the magenta one, are bell-shaped also just like the standard normal distribution. And they're also symmetric about a mean of 0. So there's a lot of commonalities with the standard normal distribution. Here's where it differs. There is one standard normal distribution, whereas there are a bunch of t-distributions. It's like a whole family of curves. And essentially, you don't just randomly pick which family member you want to use in your problem. You have to figure out exactly what one you need. And that is determined by this. Right here, D period F period stands for degrees of freedom. The number of degrees of freedom is one less than the sample size for the t-distribution. So again, this lowercase n is standing for the sample size. So the number of degrees of freedom is the sample size minus 1. Now, also one other observation here. This magenta colored one has degrees of freedom 1. This black one has degrees of freedom 2. And this red one has degrees of freedom 3. As the number of degrees of freedom goes up and up and up, notice that the curve is getting closer and closer and closer to approximating the standard normal distribution. That's what this fourth key feature is here. Just like we did with our previous examples, we need to know the values of these endpoints here for a certain level of confidence C. In the previous section, we saw that this was negative z sub c and z sub c. They were the critical values associated with the standard normal distribution, but now we need the critical values associated with the t-distribution. So they're going to be called negative t sub c and t sub c. We need to be able to get this value t sub c, but we're not going to get it in the same way that we got the z sub c's. There is an actual entire table of critical values associated with the t-distribution based on the different numbers of degrees of freedom. Let's take a look at that table next. You have this t-distribution table in your formula sheet. Before we start to read it, there is something we should first notice. The values of the table, which are in the heart here, these are not areas like they were in the standard normal distribution. Notice these couldn't possibly be areas. You can't have an area underneath the curve of 3.747. The total area is 1. So these right here, these themselves are the critical values. So this is a table that's set up quite a bit differently than the standard normal distribution table. So these are the critical values, and this table continues to go on, and you can see it goes all the way up to about 100 in your formula sheet. We need to figure out which one of these numbers we need. Well, it's based on two things. One is the number of degrees of freedom, and the other is the level of confidence that you're trying to find your confidence interval for. Notice this one tail alpha, two tail alpha, this stuff right here. You can ignore that for now. That'll be part of the next topic we cover, which is hypothesis testing. So let's just say, for example, you had a problem where the sample size was 10 and you wanted to find a 98% confidence interval. That would mean that you need to go to a number of degrees of freedom of 10 minus 1, so specifically 9, with a level of confidence of 0.98. So that puts us in this column right here. So where these two things intersect, which is precisely 2.821, that would be our critical value t sub c. So c in this case is 0.98. So t sub 0.98 is 2.821. Now that we've covered the basics of the t-distribution, let's see how we can compute a margin of error for a problem like the one we started with in this video. How do we compute the margin of error E? So this is another scenario. If the population standard deviation is unknown and the data is approximately normally distributed or n is greater than or equal to 30, then you can use this formula right here for the margin of error. So let's just highlight a couple of things first. We've got population standard deviation needs to be unknown and the data is approximately normally distributed or n is greater than or equal to 30. So we need one of these two things, normally distributed data or approximately normally distributed data, or n being greater than or equal to 30. But we also must absolutely not know the standard deviation of the population sigma. Again, population standard deviation is sigma, not s. If that is the case, then we can use this formula right here where t sub c is your critical value for a given level of confidence C, s is your sample standard deviation, square root of n, of course, n is your sample size. And then the strategy is going to be exactly the same. You're going to construct your confidence interval this way, where you take x bar, add e, and take x bar and subtract e. And one other key thing that's always assumed whenever we're doing stuff like this is that your samples are random. If they weren't random, again, you couldn't apply this theory. So let's go back to the original problem and see what we can do. Let's quickly read through the problem again and then redefine our variables. So the Wind Mountain Archaeological Site is located in southwestern New Mexico. Wind Mountain was home to an ancient culture of prehistoric Native Americans called Anasazi. A random sample of 15 excavations at Wind Mountain yielded a mean depth of 74.2 centimeters and a standard deviation of 18.3 centimeters from present-day surface grade to the location of the significant artifacts. Assume the depths are approximately normally distributed. Compute a 95% confidence interval for the mean depth mu at which archaeological artifacts from the Wind Mountain excavation site can be found. Interpret your results. So, we already did this on the first screen. We've got the sample size n is 15. We've got a sample mean X bar of 74.2 centimeters, and we've got a sample standard deviation S of 18.3 centimeters, and we're doing this at confidence level 0.95 or 95%. So again, we cannot use the standard normal distribution where where the margin of error had Z sub C here because sigma is unknown in this problem. But why can we use the t distribution? It's not just good enough for the sigma to not be known, which is true. Sigma is not known here. We also need either the data to be normally distributed or approximately normally distributed, or we need sample sizes of size 30 or higher. Well, our sample size is 15, so that's not 30 or higher, so that doesn't satisfy it. But we need either that or we need the data to be distributed normally or approximately normally. And that we in fact do have. It says it here, assume the depths are approximately normally distributed. With that highlighted in red and the fact that sigma is unknown, we can use the t-distribution for this problem. Let's go ahead and find our margin of error, which is precisely this formula right here. So we've got E equals T sub C in this case is 95%, so T sub 0.95 is going to be S divided by root N. So let's plug these numbers in. Well, to get T sub 0.95, we need the number of degrees of freedom. And the number of degrees of freedom here is the sample size 15 minus 1, which is 14. So we are specifically talking about 14 degrees of freedom. And we're given a 95% confidence interval. So we're talking about this column right here. So where those two things intersect at the 2.145, that is our T sub 0.95. So we get 2.145 times S is 18.3 divided by the square root of N is 15. Make sure you plug in 15. Don't plug in the number of degrees of freedom there. This is the sample size, not the number of degrees of freedom. And if you plug this whole expression into your calculator, you get that this is approximately equal to 10.14. Once you've computed the margin of error, we need to subtract and add the margin of error from the sample mean. So we're going to do X bar minus E, which is 74.2 minus 10.14, which comes out to be 64.06. And then X bar plus E is equal to 74.2 plus 10.14, which is equal to 84.34. These are the ends of our confidence interval for mu. So our confidence interval is 64.06 is less than mu, which is less than 84.34. Read differently, the confidence interval for mu is from 64.06 to 84.34. And as always, we're not simply just writing the confidence interval, we need to interpret our results. So we did all this under the assumption that we want 95% confidence. So we are 95% confident that the interval from 64.06 centimeters to 84.34 centimeters contains the actual population mean depth. Contains the actual population mean, or just the actual mean depth of these artifacts.